Hello, my name is Koen Bertels. I'm Belgian by nationality, but I've been a professor for a long time in Delft University of Technology in the Netherlands. And now I only part-time work at the University of Ghent, but I'm basically involved with QBee, which is my third company. Yeah. This gives a quick overview of my academic research career, mostly focusing now on the quantum part. So it's already more than 10, 11 years that I'm involved in this quantum computing research in Delft. That's where it started in Europe, at least in a very important way, because it combined physics as well as engineering. Yeah, so that is I emphasize here only Intel because I managed to get Intel land in Delft because I really brought a computer architectural view, yeah, which they didn't get from Stanford, Intel, Harvard, Princeton, MIT, etc. Yeah, so what is the main reason that quantum computing is suddenly a hot topic? Because we are basically at the end of making classical computers more powerful. And that is, I will not go into the details, but the CMOS transistor, which is used as, let's say, the engine to make any kind of computer chip, is going below 1 or 2 nanometers. So once you go below 1 nanometer, we enter already the quantum mechanical universe. So that basically means that we start having completely different kind of phenomena, yeah, that we try to implement. So this was the growth of this quantum technology kind of initiative. And of course, we do know Intel came to Delft, yeah, but also IBM. Intel is putting a lot of money into it, Alibaba, yeah, and so they're all focusing on different kinds of QBee technologies. And so the goal is, of course, that we need to define both very good quantum hardware, but also envision that we start on time, which is now, to work on quantum software. The basics of quantum, I cannot explain that in a couple of minutes. It simply means that you have different, if you have a qubit here, psi2, that I say here, is consisting out of 8 base states. That means we combine 3 qubits together. Each qubit has 2 base states, so it's 2 to the power 3, gives me 8. Yeah, and these are 8 parallel ways in which any quantum circuit will be implicitly parallel executed. So this is already an incredible innovation, because if we want to parallelize things, which we're not really capable of doing in the classical machine, we need to be very explicit on every single path in the algorithm. Yeah, whereas the quantum mechanical world or universe only does that for us. Yeah, that's very, very strange to see. If you go, let's say, to 300 qubits in superposition, yeah, and that's why I have here this hydrogen cloud in space. Yeah, that means this is bigger than the estimated number of atoms in our known universe. Yeah, we have, I don't know how many. There used to be 10, now there are many more. But so just the combination of all these planets together have a lot of atoms. Yeah. So everybody in the world is using, let's say, the full stack of quantum computing. Well, that's very good. Well, I'm just happy to say that this concept really came out of our group, my group in Delft, and that made Intel convincingly put $50 million into the quantum research we did in Delft with them. Yeah, and that is still going on. Now I still focus on the full stack. Yeah, and we can of course evidently still check whether physical qubits are good. Yeah, but we also want to say, look, we need to focus much more on end user applications in genome sequencing, quantum chemistry, etc. Yeah, and then we assume that the perfect really the qubit behave in a perfect way. No decoherence, so no collapsing of all of these base states. Yeah, that we get maybe one single result. Yeah, and there may also be errors, but no errors with the perfect qubits. It's a mathematical concept, yeah, but it's a very important one. Mathematical, why? Because we can make sure that our quantum circuit is correctly executed. Yeah. Does that involve the number of qubits that we need? No, not at all. You cannot have one single miracle approach that solves all of the problems. Yeah, it's so complicated in the end, because the quantum mechanical universe is an analog phenomenon, whereas in the digital, everything is digital. Yeah, the classical is a digital machine. So I will not go into those details. When you look at quantum hardware, which was my business for 7, 8 years in Delft, Yeah, and I look mostly at Super and CMI because that was the collaboration with Intel. Yeah, but you also have, like, let's say, ion traps, photonics, and things like that. So they all have the same kind of problems, and that's why the noise that you get, the errors that you get from different kinds of QB technologies is completely different. So that is why, yeah, I think, okay, it's also important to really start looking at other approaches. Now, you see here a lot of companies worldwide working on quantum computing, and you do see like Atos, you do see like even Google, but they work on hardware too. Yeah, they work really on let's say the quantum hardware development. But I think we also need to focus much more on quantum applications. Yeah. This is Gartner, which is a very famous American consulting company. And they've always been looking at all kinds of technologies, let's say over 20, 30 years. And they discovered for themselves that there's always a hype cycle, which you see here. There's a lot of hype in this phase, incredible, amazing. This is going to change everything. Then you reach a summit here at top. Yeah, and then none of these promised results are there. And then a lot of people, and including companies, they lose their interest. Yeah, and my vision is, yeah, and you see here quantum computing is a little bit on a decline. Yeah, because we are not there yet at all. That's what I've already been predicting for several years. Yeah, but now we start looking at quantum algorithms. And again, I added myself here the dotted line. Universities, but also companies need to look in, let's say, at the next 10, 15 years, what will be their quantum competent team? What will be their quantum algorithms they will need if ever we make very good quantum hardware? Yeah, that is the main vision, how I interpret this particular kind of thing. Yeah, different vision. Yeah, I worked on the hardware in the gray box. Now I'm in the green box, and maybe in a couple of years we can test again, move the quantum software to in any physical chip, but we can also simulate it on a mathematical model. Yeah, such that maybe in 10, 50, more 50 to 20 years, we will have quantum accelerators entering the market. This is how I vision the long-term kind of approach. Yeah, so in every field, chemistry, biomedical, etc., yeah, we need to combine, let's say at a European level, but should be worldwide. Yeah, we combine companies as well as universities, yeah, researchers, research institutions, etc., to combine with each other such that we get a quantum computing logic set of concepts for chemistry, biomedical space. A lot of them will be overlapping. But for now, we need to know that whatever we do in the hardware part, we only use 20 quantum gates, 20 to make a universal kind of machine. This is, of course, not reasonably efficient. Yeah. So also there are very few quantum algorithms being developed so far. And this is an overview. It's around 25. Yeah. And you find it on Wikipedia. A lot of information you find on internet. So of course, it shows that we really need to extrapolate, yeah, and involve many more people into the quantum software development. And then we can merge again, as I showed in this picture. Yeah, we can move again hardware and software together. Yeah. So what kind of applications? Well, it could be, let's say, an atomic clock, could be optimization, the way from Canada, for instance, quantum machine learning. It can also be biomedical or chemical kind of things, yeah, while also not space. Yeah, and so these are the things that QBee is involved in. We work on space, we work on chemistry, and we work on genetics, so biomedical. Are we the only companies? Luckily not. Yeah, and hopefully there will be many more popping up. Yeah, but we need much more collaboration among these different players. Yeah. Who is the team behind QBee? You see, we all have a PhD level. Many of them, like the first three, are professors. Yeah, and the two others, they also have professorial ambitions. Yeah, but that simply takes time. Yeah, Arita just finished his PhD last year. Yeah, with me or a year and a half ago. Yeah, and so and Tamara the same. Yeah, she did the chemistry in Belgium, by the way. Yeah, in Louvain-la-Neuve, and clearly she has the competence. Yes, she's a very bright scholar also to work on these quantum computing aspects for chemistry. Yeah. So how do I see the future? I will not go into the details. There's clearly the PISC, the perfect qubit kind of driven application that we're currently doing. Yeah, there will still be, can say, physical development of quantum hardware. We still have to see how many of those qubit technologies will survive. Yeah, and remember that is what Scandinavia said. Now they say, okay, for the next 3, 4 years, everybody can do whatever they want, but then they will invite or select only 2 qubit technologies, And those, they will be developed into, let's say, an operational quantum machine. Yeah. And that is when we will have, let's say, a fault-tolerant quantum computer at some point. Yeah. So now we still need to simulate or emulate it a little bit. Yeah. But then at some point in 10, 15 years, we will have enough, let's say, results to have a realistic quantum accelerator on the market. So this is in short. NISQ will absolutely stay present. The noise, yeah, is too different from the different kinds of fields. That's why I think it's important to abstract away from these things and develop in using PISC, so the perfect qubit intermediate scale quantum. Yeah, and we can do that in all kinds of fields. So if you're interested, you can download these papers. If you Google from this to PISC, and then yeah, you will find those papers. Thank you very much.